Next, through two exercises, we qualitatively draw the frequency characteristic of the system. The first is the frequency characteristic of the series connection of the resistor and the inductor. We can write that it's a complex number, its module is, and its phase angle is. So we can draw its AF characteristic and the PF characteristic. We first draw the AF characteristic. This part is equal to 0 when frequency is 0. That is to say, the AF characteristic starts from the point R. With the increase of frequency, the inductive effect is larger and larger. That is to say, when omega tends to be infinite, the function tends to be omega L straight line. So the AF characteristic of the port starts from R and gradually tends to omega L straight line. We use a similar method to consider the impedance PF characteristic. When omega equals 0, the angle is 0. That is to say, it starts from 0. With the value is larger and larger with the increase of the frequency, it tends to be infinity when the frequency tends to be infinite. Therefore, the impedance angle tends to be 90 degrees. So we finish the impedance frequency characteristic of the one-port network. Next is the serial connection of the resistor and capacitor. Similarly, we have its module is, its impedance angle is. We can also draw its AF characteristic and PF characteristic. Look at this part. It's infinite when omega equals 0, and it's positive infinite. When omega tends to be infinite, it tends to be 0. That is, the AF characteristic tends to be R. That is to say, the AF characteristic of a serial connection of a resistor and capacitor starts from the positive infinity and tends to be R with a form of reciprocal. For PF characteristic, the value is infinite when omega tends to be 0. The angle is 90 degrees. So therefore, it starts from minus 90 degrees. When omega tends to be infinite, the value is 0 and is 0 degree. So it tends to be 0 from the negative direction. So we finish the drawing the impedance frequency characteristic of the one-port network. Next, we draw the frequency characteristic of the transfer function. The input is voltage source and output is the capacitor's voltage. We have deduced that its transfer function is like this. In order to draw more carefully, we might as well calculate several special points. We assume that RC equals 1 so as to facilitate the calculation. Then the frequency characteristic becomes a one single variable function about omega. You see, when omega equals 0, the module of transfer function is equal to 1, and the phase angle of the transfer function is equal to 0. When omega equals 1, the module is equal to square root of 2, that is 0.707. The phase angle is equal to minus 45 degrees. About the amplitude being equal to 0.707, we will discuss in detail in the following lectures. Please pay attention to it. Next, we can also write the value of the amplitude and phase when omega equal to 5, 10, 20, 100. That is. From these values, we can find that the module is decreasing with the increase of the frequency. It gradually decays from 1 to 0. Similarly, with the increase of the frequency, the phase angle gradually decays from 0 to minus 90 degrees. And we can see that in the early stage of increasing of frequency, the attenuation of transfer function is faster, and it tends to be saturated in the later stage. Phase angle is similar. According to the table, we can easily draw the qualitative curve of the transfer function of the circuit. That is